Swayam Prabha. Digital India. Educated India.
Welcome back. We just introduced the models in the previous session, the semantic models basically. Now we'll actually describe a model and also we'll talk about how to understand a model in the semantic framework. I already said why we need models. Now we'll talk about specific models and stuff. So suppose the speaker says to the hearer that if it is true that either Ram or John has killed Tom and Ram has not killed Tom, then John has killed Tom. Now without looking at the world, without looking at anything, the hearer knows that this must be true. Why? Because what the hearer has in their mind is something like this. This we call, actually this format, if we remember, this we called MTP, modus tollent opponents. We apply modus tollent opponents on these two. If it is 1, if it is 2, we just use MTP 1, 2, because this is P or Q and this is neg P. Therefore, Q must be the case. So it is, we need not look at the world to have any Ram or any John or any Tom. We just know that if this part is true, then the other part, that is this, must be true. For that we don't need any understanding of the world. Now what is the mystery of the truth of such logical sentences? The mystery actually lies in the very understanding of these operators. For example, either and or and this thing. So it actually lies in or, not, and then of course the sentential variables like P, Q, R and stuff. These are formally true. We appreciate the truth of this sentence the moment we understand the meaning of the sentence. It is because the truth lies in the structure. It lies in the very structure of or and not and their interrelation, and how something is concluded on the basis of or, not and other sentential variables. Just that, nothing else, because these are structurally determined. So the logical connectives themselves determine the truth of a sentence like this. But that is not true about a sentence like Homer is at home. This is a very different sentence. I don't know how to evaluate this sentence without having a real world. So otherwise it is a piece of fiction. It becomes a real informative sentence only when there is a model corresponding to it. So precisely when somebody says seriously Homer is at home, that person in a sense says that there is this thing in the reality. We differentiate between the language and the reality, and we can see that this Homer somehow corresponds to this individual who is there in the reality, and then Also, there exists home for Homer. There exists Homer's home. So let this be the home. But even then, this is not. We don't know whether this is. We understand that, like when somebody says Homer is at home, we understand first we can sort of pick out Homer, then home. But even then, we don't know whether the sentence is true or not. The reality must look like this. Must look like this in order for the sentence to be true. So it is not enough to have other things, and it is not enough to have Homer or a few houses and trees and the sky and the sun and the moon and everything. We also need to see whether this is the case. That is, whatever is denoted by home contains the thing, the object that is denoted by Homer. Only then it makes sense. Only then. So if this is the case, if this is the picture of our world, of our reality, then the sentence Homer is at home is true. Otherwise false. That is, if the home, this home, we are not talking about the word, if this home does not contain this object, the sentence is false. So the sentence is true only when this thing is a fragment of the reality. Otherwise the sentence is false. So this is how the entire system in a sense depends on models. Now we can see that not that every sentence depends, right? Sentence that do not depend on any model would constitute the subject matter for logic, but sentences that depend on a model for their truth value would be the subject matter of formal semantics, where logic doesn't work. And of course these two areas would definitely interface, would definitely interact with each other, and they would unite, and we'll see new things. So but the point is, we need a model, otherwise we cannot say whether this standalone sentence is true. Yes, we can anytime say that Homer is at home if Homer is at home. This must be a true sentence, but this sentence is useless because what does it inform me of the world? Practically nothing. So we are not just happy, we are not happy with just logical sentences. Also, we need to reach some truth through the logical sentences. For example, suppose evidence somehow said that either Ram or John killed Tom, and then there was evidence to suggest that Ram did not. On the basis of that, logically we conclude, without having any more piece of evidence, we conclude that therefore John killed Tom. But here we reach some truth by applying our semantic rules, both rules that concern logic and that concern rules about the model. So we apply those rules to a model. Basically, that what is our model? The real world, wherever the investigation takes place, wherever there is a Ram, there is a John, and there is a Tom. With respect to that world, which is our model, this sentence, therefore, that is John killed Tom, will either be true or false. If the sentences, the premises are true, then the sentence, the conclusion must be true, and false otherwise. So this is what we understand by a model. And so the conclusion is, with respect to a model, some of the sentences, basically the atomic sentences, will have their truth. And also, not that all non-atomic composite molecular sentences will have their truth on the basis of logical connectives. For example, we can say that Homer is at home and Maggie is at home. There is a logical connective sitting there, but that does not determine the truth of this big sentence. So there are sentences of two types, and we need to study all two sets separately. Now, as I said, we are in a position to understand, to actually study semantic models and stuff. So, the first semantic model we shall be considering is called L0. It's a propositional model. We'll go to that. Before that, just another feature of Montague semantics, especially sort of it's a so all these features are there in Montague semantics. Added to that, Montague did something monumental in this field. We just will talk about that, and in the next segment, and we'll start our model. In this segment, we will talk about, as I said, we'll start talking about the model L0. Before that, just one very important thing normally somebody misses when they start studying a model proposed by Montague. Not that Montague directly gave these models, but he gave the idea, and the textbook we are using, that is Introduction to Montague Semantics, actually has given all these models and stuff. So, now Montague's models have got a unique feature which for the first time he came up with, sort of he could successfully add this feature to his system. The feature is something we already mentioned in the first session, but that time we were not in a position to understand it fully. It was just a very quick mention, but now we are actually talking about it. So, now we'll talk about two different areas, rules of two different types. So, on the one hand, we'll have syntactic, we'll have syntactic rules for combining units to make phrases and sentences, and on the other hand we'll have semantic rules. Montague's idea is whenever we have a syntactic rule here, we have a corresponding semantic rule there. For example, in the first model, in the first language, not in the model, our language is going to be L0, which is a formal language, an artificial language. We have the following rules. So, syntactic rule 1 would say that if delta is a one place pred and alpha a name, then delta alpha is a sentence. Rule 2 will say that if gamma is a two-place predicate, we don't know what is meant by two-place predicate or one-place predicate right now, but we'll know. And if alpha is a name and beta is a name, then alpha the gamma alpha beta 2 is a sentence. And just one rule with the logical connective: if phi is a sentence, so is neg phi is also a sentence. So, just three rules. Corresponding to these three rules, you have semantic rules. You have to have their semantic corresponding semantic counterparts. For example, you have this rule which says that delta alpha, this phrase, is true if and only if the reference of alpha belongs to the reference of delta. So, here you talk about the construction rule for delta alpha, and here you talk about the truth of the construction delta alpha. And here you have, if gamma is a 2 plus predicate and alpha and beta are names, then gamma takes alpha beta, that construction, that is gamma takes alpha beta. This construction is true if and only if the ordered pair alpha and the ordered pair beta belongs to the reference of gamma. So, once again we can see that there is a correspondence between this and this. Here there is a rule for constructing gamma alpha beta, and here is a rule that interprets that, rather that assigns that the rule that assigns truth value to this construction. So, it says that it states the truth conditions for this construction, and 3 which corresponds to this rule, semantic rule 3, which says that if phi is a sentence. Now, remember that we are not doing it seriously, we are just this is a very rough representation of the semantic rules. We are not going to discuss the rules here, we are going to do that when we actually read the system. But now if this is a sentence, then this is true if and only if phi is not true. Now, you see that here you have a rule for constructing neg phi. So, on the other hand, look at the counterpart, you are evaluating the truth value of neg phi by stating its truth condition. So, and I hope we understand this phrase if and only if not we will talk about it. So, now we start talking about our first semantic system, that is L0. Remember what we said in the beginning, in the first session? We said that the semantic systems we have, that Montague said about the semantic systems we have, that there is no significant theoretical difference between the grammar of natural languages and the grammar of formal languages. Now, Montague has to prove it. This is how he proves it. First, he gives the grammar of a formal language, and then he gives a grammar of a natural language or a fragment of a natural language, and he shows that there is once again a homomorphism, that is there is once again a correspondence between the rules of this grammar and that grammar, that is the grammar of natural language and the grammar of the formal language. We will see that. Now, our L0E is a propositional language. So, it has words and it has the logical connectives. What makes it a propositional language? The logical connectives, that is it has neg, or, and, if then, and, if and only if, these logical connectives. And so, this construction of this system is this is the basic units, the basic expressions. So, you have 4 names here. Names, remember, names are not part of the reality, they are linguistic things, they are part of the language, not of any reality. So, after that they have, this system has 2 one-place predicates M and B. Also, it has two two-place predicates K and L. What is the difference? The construction of a one-place predicate is something like this. We now remember the Frege idea that a concept word denotes a function or a concept. Here, concept words are more or less the modern predicates. So, for Montague, the Frege concept words are sort of not that exactly are, but they can be understood as predicates. Now, predicates are of different types. Depending on the number of arguments they can take, predicates sort of are sort of classified. Now, and one plus predicate would look like this. You will have an individual here, I1, and you have a truth value here. You have another individual and another truth value, whatever. So, for every truth value I just write T, and then you have, yeah. So, it is basically, it looks like this. So, for example, is a prime number is a predicate. So, it takes, how does it look like? So, here is the general format, here is the example. So, it maps 1 to, I do not know whether 1 is a prime number or not, I am confused. So, it is, let us say it is undefined. Let us take 2, 2 is definitely a prime number. Let us take 3, it is definitely a prime number. Let us take 4, it is not. 5, once again a prime number, and we come to say infinity, once again it is undefined. I do not know whether infinity is a prime number or not. So, you can check whether 1 is a prime number or not. I am just showing you the possibilities. Some things may have this mapping also, but it does not matter. Now, you give it 2 as an argument, it will yield 1. So, what is the predicate? The predicate is a prime number. We can see that it is a 1 place predicate. And what is the 2 place predicate? Something like x divides y. So, is a divisor of kind of that, is a divisor of is a 2 place predicate, because it will look like this. So, among other things, it will have 4 2 mapped to 1, but 4 3 will be mapped to 0, because 3 does not. So, it is like is divided by function, is divided by. What we mean by divided by is equally divided by. So, in when we talk about natural numbers, naturally fractions are sort of not part of the system. So, we are talking about these sets, and then once again 6 2 will be a member of it and 6 4 will not. So, like that there are many members, but you just see one thing, its domain consists of ordered pairs and its codomain consists of truth values 1 0 and stuff like that. So, this is a 2 place predicate, because it will not give you a truth value unless you give it 2 arguments in a specific order. So, so this is the difference between a 1 place predicate and a 2 place predicate. I hope we understand what is now going on. So, M and B will be here and K and L will be here. Now, the rules, syntactic rules, the formation rules. If delta is a 1 place predicate, so delta can take only a 1 place predicate, nothing else, and alpha are named. Remember, just very briefly write, our names are D, N, J and M, D, N, J, M. We have 2 1 place predicates, that is M and B, M and B. We have 2 2 place predicates, L and perhaps K. So, this is it is a very small language having just 1 2 3 4 5 6 7 8 units, nothing else. So, the units will now unite to make phrases and sentences. Now, the first rule says if delta is a 1 place predicate, so delta must be here delta must be choosing something from here, and alpha a name, then delta alpha is a sentence. So according to this, by following this rule, we can make things like, so we can take M, which is 1 plus predicates, and a name, so we can have MD. So MD is a sentence, or if we keep taking M, MN is a sentence, MJ is a sentence, or MM is a sentence. And now if we take B, it will be BD, and BN, BJ, and BM. So as far as the 1 plus predicates are concerned, you cannot make any more sentences, only 8 sentences you can make. Now we go to the second, and that says that if gamma is a 2 plus predicates and alpha and beta are names, then gamma alpha beta, which is this structure, is a sentence. So now we can take LK or whatever. Now we have a lot more sentences in this segment. So for example, we can have L. Now remember, this is very important. They have not used, they have, for them, this bracket means, in this semantic system, this bracket means that they are in this order, but not everywhere. Means here we just stipulate that here alpha beta must be presented, must be sort of kept all the time in the order given. So whatever order is here. So gamma alpha beta can be instantiated as like this, D D or D N or D M, many things, and K similarly D D or K N D. So the point is, this must be a 2 plus predicate, and this must be a name, and this must be a name, and 2 things must be there. So if we follow these rules, you can make all these things, and whatever M, all these things we can make. Just follow the rule and make things. And then you have the third rule, that is, if anything is a sentence, then the phi is a sentence, and so phi will now collect its phi is a variable, but the variable ranges over sentences. So these are the sentences available, not that these are the only sentences available, but these are the sentences available so far. Now with the help of these, I can now make, we go to the next level. If MD is a sentence, so if phi is MD, then we can have neg MD. We can have, because LDN is a sentence, now neg LDN is a sentence. Because KND is a sentence, neg KND is also a sentence, and stuff like that. These are sentences. So these are actually the base steps of our recursion, and this is the first recursive step. We can have these things. Now notice that this is a monadic operator. This can take just one sentence. It cannot take more than one sentences. Then these are dyadic operators. Dyadic operators work in a different way. So they take 2 sentences, not one. So then if phi and xi are sentences, so is phi and xi. So we understand that we take, for example, say this is phi. So we take this sentence. By following this rule, we can make, and we take this sentence and neg LDN. This sentence we make by following the rule 4. So by following rule 5, we can make this sentence. We can have neg K D N, or just something very simple, MD. So now you can have many sentences because you are introducing logical connectives. So, this is and, this is or, you need not interpret these as and or and stuff, but then they actually would mean these, because we will see the semantic part. And then we come to this, which says that if phi and psi are sentences, then so is phi implies psi, which means if phi then psi. So, we can say that if k n n is true, then neg L D n is also true. So, we can make this sentence. And finally, we need to talk about it a little. It is if and only if. So, anywhere we can write if m m. So, m m if and only if b j. Suppose we are choosing any random sentence. So, these are all sentences. So, we can have this. Now, what does it mean? Actually, it can be paraphrased as the following. The moment you write this, you are actually writing that it is true that if m m, then b j, and if b j, then m m. So, actually this two-way, this this right left arrow abbreviates these two things. So, it means that this implies this and this implies this, if and only if. So, this is true if this is true, and this is true if this is true. So, it means that they are equivalent. If one is true, the other one has to be true. If one is false, the other one has to be false. This is the meaning of this thing. So, this is how we can make these sentences. And so, now not just these sentences, you can understand, you can make infinite sentences by using this, because now once this is a sentence and this is a sentence, I can just add these two through or and make this sentence. I can say that m m, I am adding this one, and neg L D n, or I am not adding this one to this m d. Now, this is a perfect sentence. Now, can you see recursion here? So, the first step of recursion, the base step, gives us these sentences, and then the second level recursion on the one hand gives us these sentences, and on the other hand these sentences, which are more complex, because these sentences will have one component, these will have two components. Now, we can go to the third level of recursion, and we can make much bigger sentences. This way we can make sentences of infinite length and also at the same time infinite types. Now, we go to the semantics of L0. We have seen that L0 has these basic expressions. It has D, N, J, M. These are names, and we remember that it has two one-place predicates, and it has K and L that are two-place predicates. So, this is the complete picture of it. Now, we shall see the references of each and every basic expression. First, the reference of D is Richard Nixon, this one. Now, let us see what this means. Basically, this means that let us pretend that Richard Nixon is not a name, it is the person Richard Nixon. D is his name, and then N is a name, but Noam Chomsky is not a name, it is the real person. Let's assume, let's pretend that this is a real person, and the same about John Michel. And finally, M is Muhammad Ali, and M is the set of all living people with moustaches. the reference of M. The reference of B is the set of all living people who are bald. The reference of K is the set of all pairs of living people. Now, this will look like, now this is the set talk, and this will look like this in the set thing, something like x1, x1, y1, x2, y2, and x3, y3 through xn, yn. But these are sets like this will have x1, x2, x3 through xn. So, these sets will look like this, and these sets, the references of 2 place predicates will look like this, whereas this is given. So, Richard Nixon, Noam Chomsky, these are individuals of the system. Now, we can see that it is homomorphism. Homomorphism is a one relationship between any 2 sets. So, we have seen homomorphism in the case of the syntactic and semantic rules. We will see the same thing here once again, that now the homomorphism is between the linguistic elements and the elements of the reality. How? So, these are sort of philosophical points, but we need to consider all these things when we do semantics. So, the point is, this is something like, this is language, this is language, this is part of the subject. The language uses mind. So, what I mean by that is somebody who uses the language, right? It is part of their mind. It is part of somebody's some living being's community. So, this person says, and there is somebody else to understand all these things and all that stuff. So, this person, suppose this person says that M D. This person says that, and now notice that M and D both belong to language. They do not language. Now, let us consider language as a technical word. We are not saying a language. Language means one set. So, let us call that set language, not a language. So, so this will be all these things will belong to the set called language. On the other hand, in the reality, how does the reality look? The reality looks like this. The reality, instead of having some person or something, it has Nixon and Chomsky, Michel, and Ali, and instead of having properties or predicates, now it has sets. Sets of 2 types, either sets like of individuals or of sets. So, now this would be the picture of the reality we are talking about. Now, can you see that this red part is already our model part. So, corresponding to each and everything. Now, so this is a linguistic unit D. Corresponding to that, we have this thing, it is an object, and then this is a linguistic entity, that is N. Corresponding to that, you have this object. Thus, there is correspondence everywhere, and I don't know, who has moustache and who doesn't have. So, I can't actually draw a picture of the reference of M here, but anyways we shall be able to do that when we do the other models, the advanced models and all that stuff. But now we'll go to the semantic rules. So the point I was trying to make is the reality or the model here consists of Richard Nixon, Noam Chomsky, the things, that is the objects, John Michel, Muhammad Ali, and some sets. So basically even sets do not exist in that sense. Sets are, so if the individuals are there, sets are different arrangements, different groupings of those individuals. So that the only that differs. So precisely you could have this reality, it's something like that. So you could have this Richard Nixon, this is Richard Nixon, and this is Noam Chomsky, say, and this is John Michel, and this is Muhammad Ali. So I just say that one set has these members, and then I can say that another set has these members and nothing else. So it is all about changing the group, that's it, and I will define sets on the basis of that. So basically what exists is this thing, that is NCMA. N, which is Richard Nixon, C, Noam Chomsky, M, John Michel, and A, Muhammad Ali. So the reality actually consists, the model consists of just 4 objects, and groups are defined on the basis of those objects. Those groups are our sets. So also we can define now K. Suppose Richard Nixon knows Noam Chomsky, but Noam Chomsky does not know Richard Nixon. Suppose in that case this thing will be part of, suppose John Michel knows Muhammad Ali, but Muhammad Ali does not know John Michel. So all these things once again will define another set, and suppose nobody else knows anybody else in the system. So once again you see it is another arrangement just of objects, individual objects in the reality, nothing more than that. So this is our, this is the red part is our model, whereas the other part, all these side, these things, all these side things that are there in this side are our language, and we are trying to determine the what does formal semantics do. Actually formal semantics tries to understand the relationships between elements of this set and elements of this set. We'll see that, we'll see how it does that. And finally L is the set, the reference of L is the set of all pairs of living people such that the first loves the second. Now we go to the semantic rules. So we have got a construction delta alpha, we have seen that by following the syntactic rule 1 we construct delta alpha. Here is the truth value of it. We are saying that the truth value of delta alpha is 1 if and only if the reference of alpha belongs to the reference of delta. Now we can say that suppose among these people Chomsky and Richard Nixon, let's see this, Chomsky and Richard Nixon are bald, which is not true. Definitely Chomsky is not bald, but let's assume that both Chomsky and Richard Nixon are bald. So in that case we can form a sentence like by following this rule we can form a real sentence like B N. This is our sentence. Now according to rule semantic rule 1, B N is true, that is the reference of B N is 1 if and only if the reference of N belongs to the reference of B. And we have already said that the reference of B is actually this set. It is Richard Nixon and Chomsky. Now, all I do is I just replace the values. So, this is actually if you see this here, you put the value of it. It is actually Chomsky. They have written Noam Chomsky full. I am not doing that. I am rather capitalizing the name and writing it, because I am I'm removing some part of it. I am taking only some, so I am just trying to compensate. Okay. If Chomsky belongs to the set Nixon, Chomsky. Now, we can easily see, we can verify, we can tell that the sentence the sentence Bn is true with respect to the model we are talking about. In our model, this is the reference of B and this is the reference of N. If that is the case, then with respect to that model of ours, this is a true sentence, and a false sentence would be something like Ali belongs to. So, this is not true. Because this is not true, because Ali does not belong to this set, the sentence BM will be false. It will be false because this is not the case. Because it does not hold, this sentence will be false. This is how we understand now these things. So, then when we come to the 2 plus predicates, it will be slightly different. We need some space, that is why we are doing this. Yeah, just I want 2 more seconds for doing it, because I need to make some space here. Okay. Now, semantic rule 2, that is, now we are talking about this rule. If gamma is a 2 plus predicate and alpha and beta are names, then gamma, alpha, beta is true if and only if this. Now, we predefine, once again we define, so gamma stands for only 2 plus predicates, and we have 2. We have just L and K. So, let us elaborate on K. Suppose we are defining it, not that it is given. Suppose the reference of K is this. So, our world, our reality is such that Chomsky knows himself. So, we write this, and at the same time Richard Nixon knows Chomsky, and say Michelle is the spelling right? Yes, Michelle knows Ali. Nobody else knows anybody else in the system. So, Chomsky knows himself and he does not know anybody else. Richard Nixon knows Chomsky and nobody else, not even himself. Michelle knows Ali and nobody else. Ali does not know anybody. Say we just define K this way. If this is the case, then what will happen? We need to now understand. So, we have this construction gamma, alpha, beta. Gamma stands for a 2 plus predicate. So, naturally we are going to select K, that is the reason we have chosen k, we have defined k. So, we take k. So, the sentence k, then we take an alpha and a beta. Alpha is a name, so I just take anybody, I take n, comma, for beta I take randomly, I take just j, I take just j. Let us check. I do not know whether this sentence k and j is true or not, but let us determine its truth value. How to determine? So, this means this is true if and only if this set, that is the ordered pair n and j belongs to this set, that is the set k. Without doing anything, we can check, because n stands for Richard Nixon and j stands for John Michell, and then we need to find that pair here, that is Michell, that is Nixon Michell. Do we find it? No, we find Nixon Chomsky, not Nixon Michell. Because we do not find, it is definitely 0. So, the truth value of this sentence, that is k n j, is going to be 0, because it does not yield the truth value 1. And once again, it does not yield because of this set membership, because this set, that is Nixon comma John Michell, is not part of this set. So, now we go to the predicate for the logical connectives, and we shall see what happens. Now, we are at the level of logical connectives, and then we will see how sentences would make sense now. The truth value of the truth value of these things are not given here. They are once again, so they are practically introduced syncategoriomatically. That is, we have not given the separate truth value for this unit. Rather, we have said the truth value, we have told the system how to determine the truth value of the whole system without knowing the truth value of this part. This is called the syncategoriomatic introduction of a segment. That is, I am not separately treating this part, but together with this, that is neg phi has got an interpretation in my system. So, so that is the reason I do not need that part. We will talk about that in the next segment. We will see that even this small thing will have a meaning. So, now we can take any sentence. We already considered a sentence like k n j, that is Richard Nixon knows John Michell. We also have seen that this sentence is not true. We have seen that. So, this is a sentence, and that actually what I said is a nickname, that is an interpretation of the sentence. Do not consider that very seriously. This is the real sentence, and that is for our convenience, that tells us about the construction of k and all that. We know that this sentence is false, it is not true. Then we need to see what happens as far as its truth value is concerned. By using this sentence, we construct this following rule 3 of syntax. And then what will be the truth value of this sentence? It will be 1 if, according to the rule 3 of semantics, if and only if the sentence inside is false. We know that because this is 0, we have seen that, we have calculated, because this is 0, the truth value of this big sentence, that is neg k n j, will be 1. This is how we determine the truth value of this sentence. Then we go to, so this is a monadic operator. Now we go to a dyadic operator. Say we go for this AND. we know that this is a false sentence, and we decided that Chomsky was bald. You remember that we decided that Chomsky was bald, although he is not. So we have assumed that the sentence B n is true. We just have assumed. Also, we have assumed on the basis of our presuppositions, on the basis of our definition of no, that is K, we also have seen that this is a false sentence and this is a true sentence. Now, not that they are actually true or false, but just we assume depending on our model. Now, let us consider a sentence like, so by combining these two through this, we can have K n j and B n. What will be the truth value of this? According to this rule, the truth value of this is 1 if and only if the truth value of this is 1 and the truth value of this is 1. Now, both conditions have to be fulfilled because we have an and here. We understand that it is not possible because this is a false sentence, although this is true, this is false. Because both the conditions are not fulfilled, we must say that the truth value of this big sentence is 0. What happens when we replace this by this, by or? So, there the condition will be like this. Once again, it is a replacement. We just say if and only if this is the case, or this is the case. If one of them is true, at least one of them is true, then the sentence will be true. So, then we can erase this. We know that this sentence is true. Because this is true, we can say that this entire sentence will therefore be true. So, we see that K n j and B n is a false sentence, but K and j or I forgot to replace this also. I have to write or here, but K and j or B n is a true sentence. So, in the next session we will determine the truth values of if then and if and only if, and then we will go to the next language, that is the English, the natural counterpart of the formal language we have already discussed, and that will somehow establish the correspondence between a formal language and a natural language, and that will sort of help us establish Montague's point that there is no significant difference between the grammar of the natural language and that of the formal language. Thank you.